Okay, so we'll start to understand the hidden Markov model and its issue with the evaluation problem in a very basic way from scratch. Okay, so first of all, what is a hidden Markov model? So in a hidden Markov model, there are some hidden states, those are not observable, and there are some visible states. Let us call the hidden states as W. These are sequence of states, so we can write them as a temporal, like from starting from a particular time instant t equals to 0 to t equals to t. If there are discrete hidden states, we can write as w1 to wt, and each of this, okay, one should be okay. Each of the states will have a different value from a subset of all possible states. Let us assume that comprises of omega 1 up to omega n. That means number of maximum possible states are n. So w1 can take either value of this, w2 will take either value of this, w omega or w whatever, or wt will take one value of any value from that state. And now we have a visible state that comprises of v1, v2 up to vt, and it again comes from a discrete number of states. Can I write that as vm? So it has m number of states, and at any particular time the omega 1, the states, the first state, can transmit from can have an emission probability of v1 to v2 to vt. Any of that it can transit, and these are denoted by b, the state it is transmitting from 1 to, so I call it as I call it as jk. So that means from state omega j to state vk, the probability is bjk, and it can also transmit next state up to a certain probability. So there is a transition probability. It can transit to any of the state. So omega j to omega j plus 1, just to indicate that it's transiting from j to j plus 1, and we call that as aj plus 1 state. It comes from j. Okay, now these are the hidden states. At each hidden state we can observe some visible state, vk plus 1, let's say. Again, there will be a hidden state, there will be a state k plus 2. Now let us assume we have observed certain number of visible states in a sequence, and that comprises of this t number of t is the number of visible states that we have observed. Now we want to evaluate, because this is a hidden Markov model HMM evaluation problem. So it can have three type of problem: evaluation problem, decoding problem, and the last one is the learning one. So this is the first step of evaluating that whether what is the probability of observing a particular sequence of some length. So that we write down by probability of observing a particular sequence. When we write vt, that means we have actually observed some v's. So I can write it as the length is t, I can write it down as t. So the vt, a particular sequence, given I know theta is nothing but the fact that we know about all the state transition probabilities, we know about all the emission probabilities, we know how many hidden states like this n can be is possible there, and how many maximum number of visible states are also there. So that is known. Aij's are known. So at the any state I know a particular hidden state, it can goes to any other hidden state with what probability? We know that. We know bjk. Given a particular hidden state, we know it can go to any of the visible state with what probability, and we know how many hidden states are there, we know how many visible states are there. Given this is known, we want to evaluate this thing, the vt, the probability of observing a particular sequence, and we will now talk about this. What does it mean? Okay, so given we know this, we can now write it down something like this. Vt, we can have many possibilities. So this is a problem of sampling without replacement. So I can write it something like, I'm picking a particular sequence of that I'm calling as Vt out of the all possible sequence of we can have. So we can think of at particular this V1, it can, how many values it can take? It can take from V1 to Vm any number of values. For each of the selecting of one particular value, V2 can also take from V1 to Vm. And if we go like this, we can have empty number of possible sequences of V's, and we are picking one of that particular sequence. And for that particular sequence, we can have same way empty number of possible sequence. We will explain it now what it is, what I mean here. So let's say we are particular about a particular visible sequence. So Vt is that sequence. How many possible such sequence? So first instance, it can be V1, V1, V1 up to V1, and this length is t. Always the number of things can fit here is discrete, and there are m symbols. So if we think it as a sampling with a replacement problem, and in between it can have how many? M to the power t sequences. It can have so many subsequences, and out of that we are picking a particular one somewhere here, that is Vt, and these particular sequences, for each of such sequence there can be n-t possible sequences of W's. So if we pick one such Vt out of the all possible visible states we can have, then the omega can be written something like this. Omega equals to, we start same like omega 1, omega 2, the length here is again t, and there is n, so the last state can be omega n dot 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 omega n. And how many of such sequences can be possible? N to the power t. So one thing is very clear, we look for a certain probability, this probability, and we have to check that probability for all possible such sequences that can happen. This transition of the omegas can happen. And now I can simplify the problem something like this. I can think both as a two-dimensional random variable where I can draw axis like. So let's say this is my x-axis and this is my y-axis, and somewhere I have the probability of the joint distribution of x and y. And we can think each of these sequences as some value that a random variable x can take. So this will x equal to x1, next one will be x equal to x2, and the last one will be x equal to x nt. Okay, we should not write it like this. Okay, and write it like nt. And similarly, we can think this one as y equals to, now this should be small, this should not be small, it should be, this is a random variable, it can take a particular value y1, a random variable can take a particular value of there is a connection, so I draw it like this, and the last one y of mt. So this random variable y that I'm talking about, it can have values from y1 to m to the power t, and that comes with y. So 1 2 3 da 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 da, and the x will come from x1 to xn to the power t. Now for I pick a particular string from here, and that is my visible state. I can call that as, for simplicity, what I'm looking into, y v of t, where this v of t is nothing but a numeric value of the particular random variable that it can take. It's somewhere here, and I'm looking for the probability of this particular event, and that is dependent on the other random variable x that can have these many possible values. And basically what I'm looking here, this thing p of vt given theta, don't think it as a event, don't think it this is a conditional, this is not a conditional thing. Theta is not a random variable, theta is a hidden Markov model that has the known values of a, b, n, m, everything. So basically we are looking into pvt, and we can remove this theta. This is the conventional way that we write it. So pvt is nothing but, what is mean? It means that this particular sequence, what is the probability this particular sequence? So we are looking into a marginal probability distribution of the random variable y that can take that particular value out of all the possibility here. So somewhere yvt will lies here, and that is a constant. So that event out of that in this three-dimensional space of probability, this is a constant event, and in this constant event y equal to y vt, so I can write it down, this thing here, y equals to I can write it down, y equals to y vt. It will be a joint distribution, there will be a joint distribution of this random variable taking this value with the possible values that x can take, and x can take here starting from x1 to xnt. And if we look the probability distribution, they will have discrete jumps coming out of this z-axis that will give, so what this will give, this will give the probability, this one will give here the probability of y equals to y of vt given, I should be careful with the nomenclature, x1, this one, and the next one will give me x equal to x2, the next one will be x equal to x3, up to I can go here. This one will give me p of y equals to y vt given x equal to actually I have to multiply by p of x equal to x1, because this will give me the joint distribution of that line coming out of here. So I have to multiply it with x equal to xnt multiplied by p of x equal to xnt. So we are looking this thing. This thing is nothing but marginal distribution of a random variable. That random variable there is nothing but conditioned on other random variable x. This x is nothing but these are the x's. These are the x's. So for I can write it, just writing is at a total law probability. How can I write a total law probability here? I can write p of y equals to y is nothing but p of y equals to y, that is an event. I can think of it as a b event, is probability of that event given another event. If it is dependent on another event a, I can just write it down, x equal to x, that is a given a, multiplied by p of x equal to x plus p of y equals to y given x not equals the rest of the event where x is not this, or I can write it as a complement into p of x not equal to x. This thing is a complement. Okay, so p of b equal to p of b given a multiplied by p of a plus p of b given a complement, p of a complement, and this is basically the law of probability. Now what we can understand from here is a complement thing. So given we know like x1 happened, what is the a complement? So x equal to x1, we can think it as event a, and a complement will be the rest of the thing, right? Now if we take two events as a, the rest will be a complement. So to think it, I can write it down as a law of the probability here. P of x equal to x1 plus p of x equal to x2 plus p of x equal to x3 and so on up to this thing. So this will nothing but, this thing will be simplified now. I think I can remove it. Okay, this thing will be written as p of y equals to y vt, that we are looking into that probability given we know that x equal to x1 and we have to multiply it by x equal to x1 and we have to go on. We will do the x2 here, x3 here, x4 here, dot 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 dot. How up to what we will go? We will go up to p of y equals to y vt given at the last point it can take x equal to x and t. I have to write it down, capital X equal to small x and t, and the condition on this multiplied by the marginal probability of that particular event. So it will become x and t. Okay, so this thing I have to now write it down in terms of w's because we know the theta with the, so here was a theta, I removed it. What theta? Theta is nothing but the aij, bij, m and n. So aij, bij, these are the probabilities of transition probabilities. Aij, w1 to w2, w1 to w3, these are the aij's, we know that. So we have to write this, we have to wipe out the x's and y's from here. Y might stay, but we don't care. We have to wipe out the x's from here. We have to write it down in terms of the w's because we know this aij is nothing but probability of w is currently in, what is the probability of staying in Wi given it was in Wj, and Bjk, it is in state W K Wj, sorry, it is in Wj given we have writing. So it is in V J given, okay, yeah. So these are the probability of observing a particular symbol given it was emitted from a hidden state, and these are the hidden state transition probability. So we know this thing, we have to write it down in that form. Now this one, x equal to x1, it is nothing but this sequence. This x equal to x1 is nothing but this sequence. The probability of observing the sequence is nothing but multiplication of the state transition probabilities in that sequence, right? So x equal to x1 is giving me the probabilities of w1 to w1 to w1 to w1 to w1. X equal to x2 is the probability multiplied by w1 to whatever the sequence is there, and in that sequence we will have a state of transition probability. So how many probabilities I have to multiply? There are t sequences, t states. So for each pair of states I will have I have to multiply the state transition probability. So there will be this term, there will be pi, and it will go from 1 to t times I have to multiply the state transition probabilities for that particular event, and this will be omega t, and I have to write it t equals to 1 to t, omega t to t minus 1, starting from omega 0 is the initial state. So p of omega t given it was in omega t minus 1. So this is nothing but this probability of being in one state given it was in the previous state. We have to multiply this state transition probabilities t times, and what about this term? This term will be nothing but in terms of b, and we can write it down as probability of, given these state transitions has occurred, what are the emission probabilities at each particular state. So at each particular state it is in omega t and it emits a particular symbol bt at that particular vt. So this thing will just becomes probability of omega t, and it emits vt at that particular state, and I have to multiply for t equals to 1 to t. So at every state it will emit some v, that states will emit some v, and if I multiply that thing and then I do the summation. So for the first value, so this is a marginal probability distribution of that sequence. That marginal probability distribution will have these many number of distinct events, and they are, each of them will have two terms because of the law of probability, total law of probability. The first term is the conditional one. So that event conditioning on this y-axis multiplied by that event's marginal distribution. That marginal distribution is nothing but the state transition probability is multiplied, and this one, the conditional one, is the emission probability is multiplied, and when we club them together and we have to sum it up, we have to sum it up to how many times? This times. So 1 to up to nt times, that the maximum number of possible sequence that can have. So let us see we have understood it clearly or not. So I can write it down in terms of a formula. Okay, how can I write it down? So let us use the red color. P of y equals to vt. This one is a smaller. Given theta, I'm writing it down that I know all the a and b's, and this is the thing I want to know. So I'll write it down in, yeah, equals to, how many terms were there? 1 to nt. So I have to put a summation. And let us call this running variable as r, and that will go from 1 to n to the power t. We are clear here? So this term I can write it down as something like p of y p of y equals to y vt, x equals to xr, that gives me xr, and I can write it down as multiplied by p of x equal to xr. Is this clear? Let us remove this part. So now for this term comprises of two things, this one and this one. There is a multiply sign here, so I can again simplify this equation into summation of r equals to 1 to n to the power t, that is the number of possible sequences this w can have. And my first thing is the how many transition probabilities are there. So every time we have what we have seen, the term I have just now wiped out, that has also multiplication of t terms. So there will be a term t equals to 1 to that, and here I will have two things. Why? One for this, the transition probabilities, another for the emission probabilities. Sorry, this is one for the emission probabilities, one for the transition probabilities. So this one I will have this term here. What is the probability of that, given it was in state t, given it was in the state t minus 1? So I can write it down as, using the blue color, p of omega t, given it was in omega t minus 1, that is the state transition probabilities of the hidden states. And then I have this term, that is the emission probabilities. So it was in state, I am watching the visible state t, given it was in omega t. And if I now multiply this, that is my this is nothing but my probability of Vt given my hidden Markov model theta, and I have just evaluated this model in terms of the A's and the B's. This I know, the emission probability B, this I know, the transition probability is A, and I was really confused how someone write this formula directly without introspecting in the deeper details of the problem.